All right, welcome back. We're going to look at day 2 of section 4.2, and today we're going to take a step back and kind of think about our geometry days and some formulas that we had from geometry and approximate the area of a region under a curve. And we're going to look at 4 different methods. We're going to look at the inscribed, circumscribed, midpoint, and trapezoid method. But while we're doing those, we're going to look at the AP notation that we're going to be expected to use, and at the end I'll show you how to use our calculator programs in order to be able to find these 4 methods. So what are we going to ask you to do to be able to approximate the area under a curve? We know that if we're given a nice geometric area or figure, a rectangle or a triangle or a trapezoid, those sorts of things, we can find the area of them. But what we want to do in calculus is be able to estimate and actually come up with the actual area that's created when one of the sides is not necessarily a nice straight line. What happens if it's a curved line? So that's what we're going to look at approximating today, and then this will lead into being able to find the actual area later on in the coming days. So let's give you a function, x squared plus 1, and we're going to approximate the area of that region created with the x-axis on the interval from 0 to 4. So if I think about the graph of x squared plus 1, x squared plus 1 is going to come in here like this. This is going to be 1, it's going to be on the high side, but you get the picture of it. We're going to have the interval from 0 to 4. So we're going to create it with that x-axis, so here's going to be our region. And we're looking for the area in this region. In the inscribed method, we call this also the lower sum or little s of n. What we're going to do is we're going to cut this into regions. And the number of regions that we use is arbitrary. We can cut it into 2 regions, we can cut it into 10 regions, 1,000 regions, and eventually we'll come up with an infinite number of regions. But for today's sake, what I want to do is go ahead and cut this into nice increments, and we're going to cut them in 4 increments. So we're going to cut it at 1, 2, 3, and at 4. And what we're going to do is we're going to create then smaller regions of this graph. For the inscribed rectangles, what we're going to do is we're going to create rectangles on the inside of the graph. So we go here from 0 to 1. We're going to take the lower or the shorter bar here, if you want, and we're going to create a rectangle within that region. Then we're going to go to 1 and 2, and we'll create a region there as well. So notice I'm creating rectangles on the inside of this figure. And I choose rectangles because I know the area of a rectangle. Area of a rectangle is length times width, if we're studying our note cards and we've been paying attention to those. So what is the sum, or what is the area of each of these regions going to look like? So our little s of n, and it's going to be our notation that we're looking for. Oh, I don't know why I put 2 parentheses there. So little s of n is going to equal the value that we get when we plug in 0 into the function. So f of 0, and we're going to multiply it by the change in x. In this case, our change in x would be 1. But we're going to put delta x there for now, for our notation. To that we're going to add, we're going to find the height between 1 and 2. In this case, our height at 1 is going to be the value, and it's going to be 1 wide, or again, our delta x. Notice our delta x is going to be the same all the way through. And then we're going to find the value at 2, because that's going to be the length of this side, and then our delta x. So f of 2, delta x. And finally, we're going to add the value at 3, again, multiplying it by the change in x, which again, we have 1. So little s of n is f of 0 delta x plus f of 1 delta x plus f of 2 delta x plus f of 3 delta x. This is a very important notation and equation so that we understand what's going on within this. And this is what I'm going to be looking for as I grade your papers. Not necessarily that you have the right answer, because we're going to put it in a calculator, but we're going to be able to find that value. We're going to be able to write that equation out. So what is f of 0? If I take 0 and plug it in, remember this is our f of x. So f of 0, 0 squared plus 1, gives us 1. And our delta x, again, our change in our x, we're always going to be in 1 unit here. So it's going to be 1 times 1. F of 1 is 1 squared plus 1, which is 2 times our delta x. F of 2 is going to be 5 times delta x, which is 1. And f of 3, we have 9 plus 1 gives us 10 times 1. So I have 1 times plus 2 plus 5 plus 10, which gives me 18. Now, what I'd like to do is go ahead and throw this into the calculator and kind of show you what we're going to have. Because we do have this notation, I do want to show you how to do that in a calculator so that you're well equipped for the exam as well. So the first thing we're going to do is hit this program button. And here is a list of programs that I gave you. If you have not gotten these programs, make sure you get them from somebody or come see me. We're going to hit number 4. And it's going to be Program Riemann. We're going to hit Enter. And what I want to do is set my parameters. So we're going to hit Enter. Our function is going to be x squared plus 1. Our lower bound, so we're going to cut this at 0. We're going to start our equation at 0. We're going to hit Enter. Our upper bound is going to be 4. That's where we're going to stop the boundary. Our partitions, I cut this into 4 partitions. Again, we can cut this in as many partitions as we want, but I'm going to cut it into 4. We're going to hit Enter. It's going to work a little bit. Now I'm going to do a left Riemann sum. And notice with this, and your graph could look a little different, but notice it's created 4 regions, 4 rectangles in there, and it's going to mirror very close to what we have on our graph. And it's going to give us that left sum. It says left sum. We'll talk about left sum and right sums here in a second, or in a little while. But it gives us that sum of 18, which is what we had here. So make sure that after you write this equation and you solve it, that you go ahead and get that left sum or that sum there for our inscribed rectangles. And at there we've created rectangles within our figure. We call this also the lower sum because notice we've lost some of our area. That's okay because we're just estimating at this point in time. We'll eventually be able to get to the exact value, but right now we just want an estimate. And we call this the lower sum because this is the lowest that we think that it could possibly be. Because it's not going to be over, because we're inside, those rectangles are inside the figure. The next method I want to look at is the circumscribed rectangles, or the upper sum. And we denote this as a big S of n. So I'm going to use the same equation. And when I graph this out, I'm going to go from 0 to 4 again. And again, I'm going to go ahead and put in 4 regions. Make it look there. So I'm going to cut it at 1, 2, 3. Again, that's arbitrary. But I'm going to cut this into that 4 regions. But now instead of going from the lowest point, I'm going to come up here and I'm going to take the highest value. So what it's going to do is it's going to create rectangles on the outside of this figure. So I still have 4 regions that I'm creating. But now my rectangles are going to be outside of that curve. So what is that equation going to look like? Now I have big S of n is going to equal, now instead of taking the value at 0, I actually come over here and get the higher point, which is going to be f of 1 times my delta x. To that we're going to add, we come over to 2, that's going to be the height of the second rectangle. So I have f of 2 delta x. Then I have f of 3 delta x. And then to that I'm going to add f of 4. This is going to be the highest point in this 4th region. So f of 4 delta x. So big S of n, f of 1. If I plug in 1, I get 1 plus 1, or 1 plus 1 gives me 2. My delta x, again, is 1 unit. F of 2 is going to be 5 times 1, my delta x. F of 3 is going to be 10 times 1, which is my delta x. And f of 4 now is 17 times 1. So I get S of n equals, here I'm going to go ahead and get 2 plus 5 plus 10, 17 plus 17 gives me 34. And this is square units as well because we're looking at the area. I guess I didn't put that on the last one, 18 square units as well, since we're talking about area. So now looking at this into the calculator again. So we don't have to do another program. We can hit enter, and it's going to take us back to our main screen. Kind of rough there to see. And now what I want you to do is hit 3, and notice it's going to create that figure again, but now it's going to create those rectangles on the outside, and it gives us a sum of 34 units. And again, we'll talk about the right sums, left sums, and the circumscribed, inscribed here in just a few minutes. All right, our midpoint rule. Here we're going to create rectangles using the midpoint of our intervals. So again, here's our graph. We're still looking at that same graph. I'm going to make this maybe a little bigger here. All right, so here's 0 and here's 4. We're going to again cut it at 4. Here's our region that we're looking at. Again, I'm going to cut it into 4 subintervals. So I'm going to cut it at 1, 2, and 4. Or 1, 2, 3, and 4. So if I create my rectangles, or my regions first, I go there. But now what we're going to do, instead of taking the lowest point or the highest value, we're going to take the midpoint. So we're going to cut it at 0.5, 1.5, 2.5, and 3.5. And what we're going to do now is come up to our function and create a rectangle there. And notice as we do this, it's more prevalent over here as we get it a little farther away from that origin. When we do that, notice we have a little bit on the inside and a little bit on the outside. And these regions are pretty close to being about equal to each other, if I were to be a better artiste, I guess. Oh, that one looks better. So notice that area there is very close to this area here. It's not exact, but it's going to be pretty close for us. So what does this equation look like? We have m of n equals, now instead of the f of 0 or f of 1, I'm taking f of 1/2 times our delta x. Again, delta x is the change in our x values, the distance between our lower bound and our upper bound for each of these regions. So that we're going to add f of 1.5 times delta x, and then f of 2.5 delta x, and then finally f of 3.5 delta x. Again, delta x, that change in the x is going from 0 to 1, 1 to 2, 2 to 3, and 3 to 4. Delta x again is equal to 1 for all of these. We'll eventually get where delta x is not always 1, so we'll have to change our notation down here. But for now, they're going to be nice clean intervals for us. So the first thing we're going to do is take a half, plug it in. 1/2 squared is 1/4 plus 1 gives us 1 1/4 times 1. F of 1.5, 1.5 squared is 2 1/4 plus 1 gives us 3 1/4 times 1. 2 1/4 squared, that's going to be 5, or 2.5 squared is going to be 5 1/4 plus 1 gives us 6 1/4 times 1. And then 3 1/4, quit out of that. There we go. 3 1/4, or 3.5 times 3.5 gives us 12 1/4 plus 1. Just wanted to double check myself there. So we get 13 1/4 times 1. Now we're going to go ahead and add those together. So we have 1, 4, 10, 24, 25 square units. And again, we can go into our programs. We can set those parameters, which I go ahead and deleted mine out, but if you still have those in there, you don't have to reset it. 0 to 4 to 4. So pulling this up, now we can do our midpoint. So we can hit number 4, and it's going to create those regions. Again, yours could look a little different than mine, but notice we have a little bit on the inside and a little bit on the outside of each of these regions. And we get a sum of 25 square units. So that's our midpoint rule. And the last rule that I want to look at today is the trapezoidal rule. And our trapezoidal rule is going to go ahead and create trapezoids. Obviously, I hope it's obvious. So I'm going to cut it from 0 to 4. And we'll cut it into 4 regions. Again, that's arbitrary, but 4 is kind of a nice clean number. I'm going to create my regions again. So I've got, again, 4 regions. But now notice, as I go from 0 to 1 and I create a trapezoid with this region, notice how these lines match up pretty close to what the actual curve is. It's not exact, but remember the idea of locally linear. A graph is locally linear. So in a small region, we can make this look very close to being the same. The curved line would be equal to that that solid line, or the straight line there. So when we look at this, it's very, very close to this region. And if we were to increase the number of regions, then we would also get a lot closer, because we get even locally, or more local, which would be more linear for us of a curve. But anyway, if we look at the trapezoidal method, how do we find the area of a trapezoid? The area of a trapezoid is 1/2 of base 1 plus base 2 times the height. Well, if I look at, say we look at this region, we call it region A. If I flip this on its side, it's going to look more like a trapezoid than what we normally would look at this and say it's a trapezoid, I think. But our A in this case would be like this. So our height is this distance in here. So our distance here would be, well, this would be 0, and this would be 1 on this interval here. So from 0 to 1, our height is actually delta x. Our base 1 and our base 2, well, that's the distance from 0, or from the x-axis up to our curve. So that's going to be the value. This is going to be f of 0, and this is going to be f of 1. So we'll have f of 0 plus f of 1. So this gets a little nastier to write the actual equation. So we're going to have 1/2 of f of 0 plus f of 1, which is our two bases, times delta x. We're going to do the same thing from 1 to 2. So we're going to take the height here at 1 and the height at 2, so f of 1 and f of 2, those are going to be my two bases. My height is actually going to be delta x for my trapezoid. So it's going to be 1/2 of f of 1 plus f of 2 times delta x. So that we're going to add 1/2 of, again we go to the third region, we're going to go 2 to 3, so f of 2 plus f of 3 times our delta x. And finally region 4 there is going to be 1/2 of f of 3 plus f of 4, again delta x. So these values, we can go ahead and find those values and find our trapezoidal sum. So I notice that we have a half in all of them, so I'm going to bring that half and I'm going to kind of factor it out for now, and I'm going to bring it back in later on. So f of 0 was 1, and f of 1 is 2, so I have 1 plus 2 times my height of 1. 2 that we're going to add. Again, remember I took that half out, so f of 1, which is 2, plus f of 2, which is 5, times my 1. And to that we're going to add f of 2, which was my 5, plus my f of 3, which is 10, and then times your delta x, which is 1. And finally, we're going to add f of 3, which was our 10, plus f of 4, which was 17, times 1. And we can go ahead and add those all together. So we have 1 plus 2, that gives us 3, plus times 1 gives us 3, and then 2 plus 5 is 7, plus times 1 is 7, 5 plus 10 is 15, times 1 is 15, and then 10 and 17 gives us 27, times the 1 gives us 1 as well. So we have 10, we have 25, we have 52. So we have a half of 52, which is going to be 26 square units. And again, in our calculator, kind of hard to see there. I don't like that view. If we hit enter, and then we hit number 5, and here comes our figure again, and we see that's very similar to our curve. We don't see a whole lot of change in those lines, but we also see that sum of 26. So that'll be our trapezoidal method. So those are the 4 methods that we will work with, and any of those 4 methods could come up on an exam, quiz, test, anywhere along the lines. Now what I want to do is talk about left Riemann sums versus right Riemann sums, and what happens when we talk about these versus our inscribed, circumscribed, midpoint, and trapezoidal methods. So the left Riemann sum is going to create rectangles on the left side, which we noticed in that calculator there. So when we did that, just a little review. If I had 3 units, I created my regions. That's kind of bad, but we create those rectangles on the inside, and that was the left Riemann sum. A right Riemann sum is going to take, again, those same units, but we're going to go, and we came across on the outside. All right, so we use the rightmost values. Well, what happens to left and right Riemann sums compared to little s and big S of n for a concave down graph? So here we had concave up graphs, which we talked about concavity in our last chapter. Here, what happens if I give you 16 minus x squared? 16 minus x squared is going to look something like that. Now, if I were to cut this into regions, doesn't matter again how many regions I cut it into, but if I were to do a left Riemann sum, notice here I would have a circumscribed rectangle. My rectangles would be on the outside of the graph. So my left Riemann sum would actually be a big S of n, where a right Riemann sum for the same graph, if I can graph just, there we go. So here, if I cut this into a number of regions again, a right Riemann sum would take the rightmost point, so it would come down here, and it would look something like that. So notice here, this would be a little s of n. It would be an inscribed equation or formula. So we'd have little s of n equals our right. So you have to be careful using the calculator programs on whether we're using the left versus the right versus little s of n or big S of n. So think about those as you're putting them into your calculator. Another thing that we want to talk about is what happens if we don't have a nice clean interval. What happens if we go from can't talk, I guess. If we take this x squared plus 1 and we were to cut it from 1 to 4 instead of 0 to 4, and we still had cut it into 4 subintervals. So here's my 4 subintervals, but now what's going to change in our equation? If I look at little s of n, now my delta x is going to change. Delta x in this case is going to be what? Well, how do I figure out what this interval is going to be? I'm going from 1 to 4, so if I go from 1 to 4, or 4 minus 1, that gives me the distance, the total distance. I'm going to cut it into 4 equal parts, so I have 3/4. So I'm taking my upper bound minus my lower bound divided by, it's going to be 4. Sorry, I did 4 units. I was thinking 0 minus 4. But anyway, so we have our upper bound minus our lower bound divided by the number of subintervals we have. Very important that we kind of see this being developed. That we take the upper bound minus the lower bound, or if you want to think of this as an A value and a B value, then delta x was equal to the B minus A divided by the number of intervals that we have. And we call the number of intervals maybe n. We'll see this coming up in the days ahead. So what would this little s of n look like, the lower sum? Well, we would find f of 1 delta x plus f of it's not going to be f of 2 anymore, it's going to be f of 1 3/4 times our delta x. And to that we can add on, so 1 3/4 plus 3/4, and then add 3/4 to it to get to our function or our notation there. All right, so that's kind of gives you an idea. A nicer way of doing that, again, is throwing it into the calculator. So we can turn that on there. We can go back and set our parameters. We can type in our function, again, x squared plus 1. And we're going to go now from 1 to 4. our partitions as 4 units, and we can do that left sum, right sum, midpoint, or the trapezoid. So maybe a left sum there, give us this, and there we go. We get 18.656 units for our area. All right. So critical information. I know it's going to be a long video here, but critical information that we want to do. Little s of n is inscribed or small rectangles. So this could be a left sum or it could be a right sum. Big S of n is circumscribed or big rectangles. We have the midpoint and the trapezoidal methods. Our left Riemann sums are going to make rectangles on the leftmost point. Again, this could be little s or big S of n. Our right Riemann sum is going to make rectangles on the right side of our graph. So again, looking at a graph, it doesn't matter what it looks like. It can look kind of weird, like if we want. If we're going from A to B here, and it could change. We could have some left and rights happening, but if we do this here, our left sum would be looking like this. So you wouldn't be able to use your calculator on this one necessarily to do little s and big S of n, but later on we'll see how to do this, where we have two inscribed rectangles and a circumscribed rectangle. All right. So then also be sure to write out your formula for the sum of the areas. This is really the thing that I'm going to be looking for, especially having that delta x in there. So write out the equation or the formula for me and throw it into the calculator in order to be able to find those areas. So good luck, enjoy. If you have questions, I'm sure you will. I ran through that kind of quickly. Please review this several times if you need, so you can kind of get an idea of what's happening. We'll practice this at a later date. Good luck, enjoy.